This is the second video lectures for shallow water waves. In our previous video lectures, we discussed the key steps in deriving the small amplitude linearized equations for shallow water waves, as shown highlighted by the yellow shaded equations. These equations can be arranged in another form or on the right hand side. So this is the starting point of this second video lectures that will start from this set of equations to derive the wave solutions, the waves that this set of equations contains include inertial gravity wave, because this is a set of equations in the rotating frame of coordinate. The rotation speed is f. Okay, so we have inertial gravity waves. We also have so-called Poincare waves, and we also have Kelvin waves and inertial waves. Okay, so starting from this set of equations, we try to solve the wave in the form of so-called plane waves. In the plane waves, we assume the waves is infinite in the horizontal plane, and the wave can be written in the mathematical form of horizontal phase lines theta, which is equal to kx plus ly, a constant phase. The k is zonal, so-called zonal wave number. L is the Mariana wave number, and then the zonal and the Mariana wave number consists of can be written in the vector form. It's called the capital K, a wave number K, which is defined as the gradient of the phase lines. Okay, so if you write the mathematical form for the solutions, for example, for the eta, which is the surface height anomalies, then the eta can be written in the amplitude part of the solution, real part of eta naught, and then the waveform, plane waveform, e to the I kx plus Ly minus sigma t. Sigma is the frequency. Okay, so you can show in the plane waveform the constant phase propagate in following the capital K directions. Okay, and oscillating in time at the frequency sigma. The mathematics of this plane wave form is explained in the lecture notes. Please refer to the note. Okay, so you can substitute this waveform into the differential equations. Then you can get a relation we call the dispersion relation, which is an equation relating the frequency sigma with the wave number. Okay, and this relationship can be written either in this form or as a function of frequency as a function of wave number in equal to plus minus square of this f square plus c square k square. Okay, so the dispersion means for each wave number there's a frequency. So if you solve for the phase speed dividing the frequency by wave number k, capital K, you get a c. Okay, and then the c is a function of wave number k. So if f equal to 0, then this is the familiar form. This is the phase speed for the gravity wave, where c naught is defined as square g h naught. Okay, but here, because you have the rotation f, so the frequency for the gravity wave is always larger than the rotation rate of rotation f. Okay, and the dispersion means for each wave number, the phase speed is different. Okay, so this is so this means that the gravity wave is dispersive. Okay, in this case, the larger uh, the larger wave number, that means smaller wavelengths, you have smaller phase speed. Okay, for the long wave, the inertial gravity wave has a relatively fast wave speed. Okay, so from this eta, in this waveform, you can substitute eta into the governing equation for u and the v. Then you can obtain the u and the v, and then you can rewrite the u v in another orthogonal coordinate, parallel and the perpendicular component of the velocity relative to the wave number k. Okay, so this is done in the lecture notes. Please refer to it again. Okay, and then you can derive this two component velocity in this cosine and sine function. So then you can see from this solution, then the u parallel square plus u perpendicular square times a constant equal another constant. So this indicates the u parallel and the u perpendicular trace an ellipse in this wave in this horizontal plane. So that means if the horizontal axis, if is u perpendicular, the y-axis is u parallel, and then because the u parallel is defined parallel to the wave number k. Okay, so this y coordinate axis also the function, the direction of the wave number k, and then as the wave propagate, the u parallel and u perpendicular is trace the ellipse in the clockwise sense, with t increasing this way. Okay, so this is a well-known property of the inertial gravity waves. So you can look at an example which is in a slab symmetric sense. That means if you assume the plane wave only changes in x direction, there's no y dependent, and then the previous set of equations for eta, u, and the v can be simplified in this x direction as a function of this is the video file, so you can see the animated solution of this x and the elevation eta, okay, surface height anomaly that oscillate in time. So you will see the video, the wave will propagate to the right or eastward. Okay, so the shading here indicate the v component, and then for this is elevation eta, so your eta distribution as a function of, in this case, eta function of as a function of cosine. Okay, and then from the eta solution of eta amplitude times the cosine, and the u, which is also the same function of cosine times a different constant. So u and eta is in the same phase. So you can think about it, for the high eta is also a larger u. For the smaller eta is a smaller u. So you can see partial u, partial x, there's convergence in this region. So you will see in the next time the elevation will increase over here. Sorry, I have to this is suppose a video file. I'm trying to show you the video. Okay, now yes. See, this is the eastward moving inertial gravity waves. As I mentioned, from u and BUDX, you see that's where the elevation will change. Okay, so and then for the U, you can see that for the higher U, you have rotational Coriolis force that will change the V component. So V is shown by for the shading. Okay, for the red color, it is away from the page. For the blue color is toward U. Okay, so you can see as the wave propagate eastward, the U and the V kind of rotation. So if you see, if you look down, the U and the V will actually trace ellipse. Okay, as I mentioned in the previous slides. So this is the plain, simplified, the so-called slab symmetric illustration of the inertial gravity wave in a constant F plane. Okay, so now we introduce another a spatial set of inertial gravity wave. That means we now put a wall at the y equal to 0 and the y equal to L. Okay, so this is so now for these plane waves, you cannot change in y direction. The y cannot be any arbitrary oscillation function with any arbitrary wave number. Instead, because of limitation, you have a wall on the southern and the northern boundary. So kinematic boundary condition or the boundary condition at the y equal to 0 and the y equal to L indicate that you cannot have v velocity penetrating the wall. So this boundary condition somewhat limited your solution. So again, now the waveform for eta, you cannot assume the sinusoidal form in y direction. Instead, you assume the eta is a function of y. Okay, but what is the function we have to solve for eta bar? Okay, so eta bar now here we can write it in as a function of a times sine alpha y plus b cosine alpha y, where alpha is from this differential equation. If you substitute this wave solution into this equation, differential equation, you will then find that there's a constant parameter alpha, which is equal to this frequency square minus rotational frequency square divided by the constant C naught square and minus K, which is a zonal wave number. So this is a constant or parameter that we use alpha to represent this parameter. Okay, so then this differential equation and from the boundary condition that that y equal to 0 and L, there's no perpendicular velocity of v equal to 0 at these two boundaries. So this will give you this relationship, and this relationship contains can be discussed, and then you can realize that there's two set of wave solutions. Okay, so this you can think about this dispersion relation, but it is for maybe several types of waves. First, for the Poincare waves or the inertial gravity wave in the presence of the wall in the southern and northern boundaries. Okay, so so from this set of differential equation, I mean the dispersion relation, if you take the sine alpha L to be 0, then that means alpha has to be a integer numbers n pi over L. Okay, and then we know that alpha is a parameter derived from this differential equation. So for alpha equal to n pi over L, then the previous dispersion relation becomes this way. So this, if you compare with the previous differential equation, is the same as this differential equation. The difference is this part. So here is the capital K square, but now the capital K becomes zonal wave number and the Mariana wave number, and then the Mariana wave number cannot be any arbitrary number. It has to be constrained by this eigenvalues, namely alpha can only be integer number n pi over L, where n equal to 1, 2, 3, an integer. So this is the zonal wave number L is now replaced by this kind of eigenvalues. The zonal wave number still remains here. So this is the same dispersion relation of the inertial gravity wave, but the Mariana wave number is modified. Okay, so with this modified relationship, and then the eta becomes cosine kx minus sigma t, which still is the same waveform in x and the t, but in Mariana direction, it is a constant amplitude times a Mariana structure, which is can be can only be a certain integer number of the cosine on sine function here. So with eta defined this way, you can then solve for u and the v. So you can also get the u and the v as the same similar kind of function, but with a different wave amplitude in y. Okay, y dependence. So this set of u, v, and eta is called the Poincare waves. So you can so now you can see this is the in this y is here is this is the y coordinate and this is x coordinate. So this is the zonal direction and this is the y direction. So the two walls at y equal to 0 and the y equal to L. Okay, so see that the Poincare waves, the inertial gravity still oscillate inside this channel. But if you look at the velocity of u and the v projected on the horizontal plane, you can see that they also they do form ellipse. Okay, and so this is so both eastward moving and westward moving waves are possible in this channel flow. Okay. Okay, now this dispersion relation contains another set of waves, which is this part. So this dispersion relation, if you take the frequency square minus c naught square and k square equal to 0, then that is looks like a gravity wave, right? C, the phase speed equal to c naught square. Okay, but this set of equation is very interesting because you can from some mathematics you can look into the notes that the surface height anomaly now becomes a cosine function of x and t, but in y direction it does not oscillate like sine cosine. Instead, it is kind of decaying in y. Okay, and then there's no v component wing. There's no Mariana flow. Okay, and then the zonal flow actually and the eta the eta changes in y, they find satisfy kind of geostrophic relationship. Okay, so because eta is known, so u component u velocity becomes the same cosine function but with different amplitude. Okay, it also has the same Mariana structure. So this is called the Kelvin waves. Okay, so if you look at the Kelvin waves, so now again, this is the y equal to 0 and the y equal to L, and this is zonal direction. So you see now the Kelvin wave at y equal to 0, the Kelvin waves move to the east, and then at y equal to L, the wave moves to the west. Okay, so this is so-called Kelvin wave, or we also call the coastal wave, because now there's the southern wall and the northern wall. So along the wall, the gravity waves propagate to the east at the southern boundary, but to the west in the northern boundaries. So this is a spatial type of gravity wave, but it is constrained that in the amplitude in y direction, it satisfies a spatial exponential form. So the largest amplitude is at the 2 watts, and it decreases in the y direction in an exponential form. Okay, so if you express this dispersion relation with number k and the frequency, the set of inertial gravity waves is shown by this set of dispersion relation for different n equal to 1, 2, 3. You have set of eastward moving and the westward moving inertial gravity waves. Okay, and then you have this Kelvin wave that is uh, uh, on the two sides. One is to the eastward moving, one is the westward moving. Okay, and then the two points here is inertial oscillation that I'm not going to talk about here, but you can look into this description about the inertial oscillation in the notes. So this is a very brief discussion about the steps that we derive the inertial gravity wave, the Poincare waves, the Kelvin waves, and the inertial oscillations. Okay, so I'll stop here.